All right, today we are starting, I'm looking for it. Today we're going to talk about tide, stuff, and transport. So first we have to do the traditional clicker question. Of course we don't have any clickers, so you just all snap your fingers. How about that? The U.S. uses, hey, wait a minute, we did this already. I thought I deleted these slides. This is an oil slide. All right, tides. So this is one of the few sustainable energy sources that does not actually come from the sun. What causes the tides? The moon, gravity, etc. So gravitational pulls, moon orbits the Earth, and we won't be using that energy up anytime soon as long as no space aliens come and blast the moon out of the sky. Here is a map of the, and look, I brought a pointer. I got 2 of these free with my television. Nobody gets that anymore. These are oceans, that's why this map looks funny. So here's the U.S. and South America, and here is where tidal power is great. Ooh, up here, oh, we don't own that. We own this. We don't own that. Oh, must be nice to live in England. Fine. Or what's over here? This looks like Africa. And this scale here goes from 0 to 140 centimeters. That can't be right. Centimeters? Here is the Bay of Fundy. This is in Nova Scotia, between Nova Scotia and another place in Canada that starts with a B that I can't think of the name of. And, huh? I can't remember. I was just there last summer and I can't remember. They have the highest tides in the world. There's the UK. They're doing pretty well. Bay of Fundy is in Nova Scotia, has the highest tide in the world. The mean is 14.5 meters or 47 feet. What? And the peak is 16.3 meters, 53 feet. Here's a map of it. Here's Nova Scotia, and I forgot what's over here. I can't remember. Don't know my Canada geography as well as I should. This is a lousy picture, but here is this dock, and here's a boat floating here, and here's the same boat at low tide, same dock. Gives you an idea. So if the tide is rushing in and out, surely we can harness that for energy. One way to do that is by something called a tidal fence. So basically in this one you have to block a channel, so you create a dam, and of course you create a dam, you can endanger wildlife and ecosystems, but the good news is the electrical generating stuff is all above water. So these things turn, the water pushes these things around, they drive something up here that generates the electricity, some kind of turbine. So the water flows through these turnstiles. Now the water is moving slowly, but it's denser than air, so it produces more energy than wind at the same velocity. But of course, water tides are very slow, but still, they do go in and out. Here's another tidal solution. This is a barrage. Interestingly, there's 2 words in English spelled the same. Barrage is a dam that is blocks the water, and barrage is a military term for when you barrage the other guys with, or have a barrage of ammunition or something like that. But this is a barrage. So here is a basin of some kind. There's a high water mark. Here's a sea. When the tide flows in, it drives this turbine. You fill up this basin, and then when the tide flows out, you drive the turbine in the other way. For this to work, you need tides of at least 5 meters. So the U.S. East Coast and West Coast are all good for this kind of thing. But you need a channel. Where does it say that? A lagoon or something. Not necessarily a channel. A third way to harness a tide is these underwater turbines. And I don't know if these have been implemented or not. These all look like computer drawings to me. But here is a thing that sits on the ocean floor. There's a giant turbine in here. Water flows in and out. And this one says 1 megawatt RTT unit, duct diameter 15 meters, duct length 19.2 meters, turbine diameter 11 meters. This is a big honking thing. And I think it will chop up your tuna fish for you too. Here are a whole set of these things that have propellers on them. So that's just another way to do it. What's the disadvantage of an underwater turbine? Corrosive environment and effect on the ecosystem. On the other hand, the advantage is you can't see them. except for the ones on the right, you can see those. Here's the world's largest tidal installation, or at least it was when I made this slide. I think there might be another newer one. This is the Reims Power Station in France. It's a barrage style, so they have a channel or a lagoon or something they can close off, and here there's a barrage here, and underneath all these is the generator. So this is located in an estuary, so they have a river, 750 meters long, 240 megawatts peak. There's 24 turbines along here. It produces, this is the peak, 240 megawatts, but on average it produces 62 megawatts. And here is a scale drawing of the barrage. So here is the road deck, here's cars, here's people, this is for scale, here's stuff, and here's the giant turbine, one of the 24 giant turbines. Wow. So what kind of tidal power is the Chesapeake Bay suited for? The answer is one where you close off a lagoon or something, so we're thinking barrage style here. Tidal power, so this is the power calculated per square meter based on the height of the tide. So here's a 2 meter tide, you might get 1 watts per square meters. This is the Chesapeake Bay in the open ocean. Here's 4 meters. 3 watts, 6 meters, 7 watts, 8 meters, 13 watts. So you see, as we're increasing evenly, these are increasing by 2. These are increasing more and more. So as the waves get high, as the tide gets higher, the power you get out of it shoots up. This is the Rance River in Brittany, France. And here's another goofy one that sits on the bottom of the ocean. This is a different style that has the propellers underneath. You can never have enough pictures. So you need specific resources like bays in the U.S. So good examples of places you might consider putting these would be San Francisco Bay, Tampa Bay, maybe the Delaware River, the East River. Chesapeake Bay is a good example. It's 12,000 square kilometers. It's really big, so even though the tide goes in and out, it doesn't fully fill and it doesn't fully drain. So maybe the tide varies by 2 meters. So if I take the area of the water and I do some conversions here, blah, 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 it works out to 1 kilowatt hour per day per person for the whole U.S. So we use the population of the U.S. here. That's the maximum potential you could get. Tidal power problems, of course, it could have an effect on the environment, particularly sea life, is what I'm thinking. You also only have this power at peak of low and high tide, so it's not peak all the time. But if you note the nonlinear relationship, we were talking about the floor, the Bay of Fundy goes at 16 meters, gives you 50 watts per square meter. So there's a real opportunity. And they don't have very many people in Canada, especially not Nova Scotia. But here's England's tide potential. Up here, 11 kilowatt hours per day per person. It's bigger than their wave potential. Remember, their wave potential was pretty good. It's significantly higher than the U.S., partly because they have bigger tidal pools. They have the North Sea. They have more ocean per person. And of course, here in Ohio, we're basically hosed. We can't have tides. We should all move to Nova Scotia or bring the Bay of Fundy closer to here. All right, moving on. Which uses more energy? A ceramic coffee mug that's used over and over again, or a styrofoam coffee cup that's used once? Let's take a vote. This is America. How many people think the ceramic coffee cup uses more energy? Nobody thinks that. Everyone thinks a styrofoam cup. Ah, interesting. Let's take a look. To do that, we're going to have to consider the life cycle analysis. So when you have a product, you have these various phases of its life. So the R phase is digging, purifying, etc., to manufacture the input. So this is creating the raw materials, basically. P is for processing. So I take the aluminum and I make it into a Coke can. U is the power used to operate and maintain. So if I'm building a house, I have some power to heat it, for example. And then there's a cost in disposing, because you have to put it in a landfill, or you have to recycle it, or there's a pollution cost. Recycling certainly takes energy. Life cycle analysis can be applied to energy use, it can be applied to toxicity, it can be applied to carbon footprint. So, for example, even if I dump something into the landfill, I still have a toxicity imprint or a carbon imprint potentially. So let's compare for the styrofoam cup and a ceramic cup. The ceramic cup, the R&P phase, 4 kilowatt hours. 70 times. Why? Oh, this is 70 times greater than the R&P phase for the styrofoam cup. So it's harder to mine whatever you make the ceramics out of and process it into a cup. It takes a lot of heat to fire the thing in the kiln. So there's a big energy investment here. Styrofoam, the stuff is made out of plastics. It's not that energy intensive. Phase U, per use. Oh, I gotta wash that cup every time I use it. So wash the cup 0.064 kilowatt hours. Styrofoam, I don't have to wash it. On the other hand, in the disposal phase, and here we don't have numbers, but we know the ceramic is heavier. That could be a factor, I suppose, especially if I got to haul it off to the dump. Styrofoam is very light, but it's more toxic to the environment. According to this, though, the ceramic is more energy intensive. Embodied energy. So the embodied energy of anything includes all the following. The energy used to produce the product, energy used to produce the materials to produce the product, so that would be your mining, refining, growing, harvesting, whatever you have to do. Then there's the energy to transport the materials to the factory, and then you also have to transport the item first to the store and then to you. Does this include building the roads? Depends on how you calculate this. We're going to look at roads separately. Energy required to dispose of a product, for example, to tear down a building. You got to have the wrecker and haul away all the stuff and maybe sort it and recycle some of it. So let's consider a simple object. Here's a soccer ball. What are the energy inputs here? Well, tell you what, let's find out. I just happen to have handy this video. What is that thing you guys taught me?
Video screen at the bottom right of the little window itself, the video window.
Oh, here?
Yep.
Thank you. I believe we have to watch this. Oh, skip ad. Let's do that.
Looks like you have to press it again.
Now I'm enraged. All right, so be watching for energy input, waste. So there's several heating steps. A lot of inking steps. I predict that went into a drying oven. were so many materials in a soccer ball. Who knew that a soccer ball was that complicated? How do I get out of this? Undo this, maybe? So, there were a lot of heating steps. There's quite a few materials in there, but what really amazed me was the number of different machines, all of which had to be designed and built just to make that soccer ball. Huge machines, giant machines. What energy uses were not included? Can anyone think of any?
Driving the plastic and the leather to the machines or the factory.
Right. Of course, they didn't show us producing the leather and the plastics and where those things came from, or the inks or any of that stuff. They also didn't show us how they packaged that, so they're probably putting those balls in boxes, and someone had to produce the cardboard for the boxes. It's unbelievable. So such a simple object, and if I owned an object like that, I would say, well, this is not energy intensive, and I would be amazed, which I was when I saw this. So coffee cups, back to that, you could say that styrofoam loses because it's a use once status, and it has more toxic inputs, benzene, and it's low density, so it fills up the landfills. On the other hand, you could say it wins because it doesn't take much energy to manufacture it. It doesn't need to be washed, so that saves energy. And you don't care if the customer steals it, so you don't stack them up on the counter at the coffee store. The ceramic cup needs to be used hundreds of times to be better off than styrofoam. Is that reasonable? Is the ceramic cup used hundreds of times? Yeah, if you don't break it. Here's a video about how making styrofoam cups is better for the environment than paper cups. You be the judge. First of all, though, evidently that's not embedded properly. No, I don't want to go there. No, I want you to play it. I don't want you to talk to me.
Hi, my name is Greg, and I'm an engineer here at Dyke Container Corporation. I'm here today to talk to you a little bit about the manufacturing processes that we use to make products like these. As you might imagine, all manufacturing processes and environmental consequences.
I need to find out how to turn this up louder. Does anyone know how to do this?
The machine next to you,
This
thing.
Questron?
Yep.
Oh. Thank you. Crestron, sorry. All right, now you can hear these guys saying.
But we believe the environmental impact of our processes to make foam cups is smaller than that of the alternative products that are available, such as paper cups. And we have many scientific studies that back up our conclusions. Many of DART's products are made of a material called polystyrene. Polystyrene is a plastic that's made from a material called styrene. Styrene molecules are strung together into long chains to make polystyrene in a process that's called polymerization. Many styrene products are used in automotive parts, in boats, recreational vehicles, toys, electronics, many other kinds of goods. For DART foam polystyrene products, we use one of two different processes. The first is steam chest molding to make our cups. The second is a process of extruding polystyrene and then thermoforming it to make plates, hinge trays, and other kinds of foam goods. I'm here at the beginning of our steam chest molding process. It's a little noisy here, but I'll try to speak loudly so you can hear me. The steam chest molding process starts with polystyrene beads like these. They are impregnated with a material called pentane. It's a gas that will puff the bead up when it's heated and make it into a foam. That process is called pre-expansion. Once the bead has been puffed into a foam, it's sent into molds in our cup machines. There, it's heated again, and the heat causes these little beads to fuse together. Once it's cooled, it will retain the shape of the cup, and that's how we make our cups. Here at DART, products like I have here in my hand, lids, plates, clear trays like this, hinge trays, are all made by processes called extrusion and thermoforming. The extrusion process takes plastic, melts it, forces it through a die into the form of a sheet. The sheet enters a thermoformer, like the one we have here behind me. The thermoformer brings the sheet to the proper temperature for molding. The sheet passes into an area where a mold clamps around it, forcing it into the shape of the product we're trying to make. When that sheet is cooled, the product is trimmed out, and we have the products we desire. That's our extrusion and thermoforming process. Products that are foamed must be foamed using what we call a blowing agent. Blowing agent that we use is normal pentane. Pentane sits inside the plastic, and when it's heated, it causes it to puff up. Think about popcorn. The pentane is like water inside a kernel of corn. And when the corn is heated, the water expands, causing the kernel to puff up into a kernel of popcorn. It's the same sort of a thing with polystyrene. DART Container has always used pentane in its cups, and it has never used CFCs or chlorofluorocarbons. It's never used CFCs or any other ozone-depleting chemical in our molded foam cups. For more information about DART or our DART products, please feel free to click on other portions of our website.
So, does this video make a case that styrofoam cups are better for the environment than paper cups?
There wasn't really any comparison, there was just kind of information given.
That's right. There was no comparison made to paper cups. So they said that they had this evidence, but they didn't present any evidence about paper cups. They also didn't tell us how much energy was used. So they weren't thinking about energy inputs, I guess, because he only talked about the pentane. But and he didn't show us any of those processes like we saw for the soccer ball. There were a lot of machines and a lot of heat and a lot of... Now this material is lightweight to transport, so they probably don't have big transportation energy costs. But we didn't see the machines in action. And we didn't see, he said the process starts with these beads. Right? We don't know what went into making those beads. So I don't understand why they believe that they're making this case about paper cups. Just saying. But that's good critical thinking, because you're right. They didn't talk about that. Everyone's got a point of view. So, of course, we're surrounded by stuff. Anything here that isn't directly an animal or a plant, and here's the animals are the people in the class, I don't see any plants. Everything else is stuff that was manufactured by somebody. So what kind of stuff does everybody use? Well, most of us have a place to live. Some of us have cars. I don't know about computers. I think we all have those. And drink containers. So let's take a look at the embodied energy and stuff. What's it take to build a house? So this is out of the book, McKay. You've got the materials here, and you've got the embodied energy in millijoules per kilogram. We like kilowatt hours per kilogram, so we kind of understand that. And he's got kiln-dried softwood, hardwood, air-dried hardwood, hard board, particle board, MDF, what's that? Medium density fiber something something. I forget what it's called. It's the real heavy stuff. Plywood, glue, laminated timber, laminated veneer lumber, and straw. Okay. Well, I hope the wolf doesn't come by and blow his house down. Stabilized earth, dimension granite, local dimension granite. So they have different embodied energy costs because the imported stuff has transportation costs. Gypsum plaster, plasterboard, fiber cement, cement, in situ concrete, precast steam cured concrete, precast tilt up concrete, whatever that is, clay bricks, that's where I thought the straw would come in, concrete blocks, autoclaved, aerated concrete. Well, that's expensive energy-wise. And then plastic. Woo! Boy, look at the energies in the plastics compared to this other stuff. Part of that is this is energy per kilogram, and plastics are generally lightweight compared to concrete and bricks. PVC is more plastic. Synthetic rubber, sounds like plastic to me. Acrylic paint. And then there's glass, fiberglass, aluminum. Aluminum is energy intensive. Galvanized steel, stainless steel. And here's a picture of a house, in case you forget what a house looks like. Here's more house stuff. Embodied energy, so here's figuring out by walls, floors, and roof. So walls, double clay brick is an expensive thing here, plasterboard line. Here's the floors, here's the roof, and then here's calculated for the entire house. 42,000 kilowatt hours of energy, embodied energy. So he figures that's about a kilowatt hour per day per person, assuming your house lasts 100 years. I think probably in England houses do last 100 years. So I tried to find out how long does the average American house last. And I could find out how much individual appliances last. And they said the walls would last 100 plus years, but your dishwasher won't. This is the body energy to make the machines that make the stuff that make the house. All that stuff's included. But it doesn't include maintenance. You're going to have to put a new roof on from time to time. You're not going to live in just the shell. You've got furniture and stuff in there. You're going to need a furnace, water heater. This stuff has to be replaced from time to time. And this is a British house. So just for jollies, I found a website that had the same data for Vancouver, Canada. This was a website that was comparing a conventional house and an energy efficient house and looking at the embodied energy. Because if you look at the making and transporting the materials, here's the embodied energy for a conventional house, 278,000 kilowatt hours. For the energy efficient house, it's more energy intensive. Probably more insulation and higher quality materials, but they clearly say it's more. Then you got to heat this house. So after the first year, you've heated this one, you've used 30,000 kilowatt hours, but the energy efficient house, you use about half of that. So it's very well insulated. So after 1 year, your total energy cost is $308,000 for the conventional house and $316,000 for the energy efficient house. So it doesn't look like the energy efficient house is really saving us anything unless we stay in the house longer than a year. If you look after 30 years, this guy was 1.1 million and this guy was 800,000. So over time, you come out ahead with the energy efficient house. 30 years, is that a reasonable house lifetime? Yeah?
Do you know what you mean by energy efficient? What's the difference?
I don't remember. But fortunately, I have the link here, so we can go find out after class, and I think it will probably describe that. I think it's heavily insulated with good windows and stuff like that, but I'm not sure.
There's just a specific rating on the entire house.
Yeah, I imagine. And my guess is that it takes more to heat a house in Vancouver, Canada than it does in Columbus, Ohio, or even Cambridge, England. Just for jollies, this was in the same source. I thought this was fun. The energy efficiency of a 2003 Honda Civic is 32 miles per gallon. The energy efficiency of riding a bicycle powered by a person who's fueled by hamburgers is 31 miles per gallon. That includes the body energy in the meat and to transport the meat. Now, a rider fueled by bread gets 300 miles per gallon. Interesting. Less embodied energy in bread than in meat. So if you have a hamburger with the bun, I guess you're coming out slightly ahead. How about a car? Takes about 76,000 kilowatt hours to make it. Say you keep it 15 years. Do people keep their cars 15 years? I see some no's. Some people do. They're saying that Americans are keeping their cars longer than they used to. So they're getting up there. That's 14 kilowatt hours per day if you keep it 15 years. I don't think the average American keeps it that long, but some of us do. 14 kilowatt hours per day. The average United Kingdom citizen owns a half a car. He does not account for this. So I looked it up for the United States. We own about 0.8 cars. And you probably want roads to drive that car on. So roads. Australian roads, I could find numbers for Australia, cost 7,600 kilowatt hours per meter of road. Including maintenance, it's more like 35,000 kilowatt hours per meter. British roads, they have 28,000 miles of roads. So if you use this number, road cost is maybe 2 kilowatt hours per day per person. But it does include bridges and tunnels and stuff like that. So just by comparison, here's road building, 2 kilowatt hours, car making, 14 kilowatt hours per day, house building, 1 kilowatt hour per day. We keep this longer. Interesting. The car is the problem there, it looks like. We should start making them out of paper cup and the styrofoam cups, because that guy said, no.
You can just throw them away.
Yeah, we can just throw them away. We don't have to pay for parking. Oh, damn, landfill. Roads in the U.S. So I can find some numbers here. We have 4 million miles of highways and streets. Wait. The British has 28,000 miles, and we have 4 million miles. Of course, we're a bigger country. Some people say that one of the reasons that we're an economic powerhouse is because we build highways early. We have 307 million people depending on the year. Assuming the same energy per cost per meter as Australia, then American roads cost about 4 kilowatt hours per day. Probably an underestimate because we had a maintenance cost in the Australian number, and I'm thinking it costs more to maintain roads in the U.S. because we have these pesky winters. So ours are maybe 4 kilowatt hours per day, and England's was maybe 2 kilowatt hours per day per person. I'm guessing that ours is really closer to 5, but it's just a guess. Personal computer. The R&M phases, so the mining and the manufacturing, 1,800 kilowatt hours. If you keep it for 2 years, how long do you guys keep computers?
That's probably the max.
Probably the max, I'm
2
hearing?
or 3 years, yeah.
2 or 3 years? I don't know what the average is for the U.S. I'm cheap. I keep them a long time until, basically I keep them a long time. But I accumulate them, and I don't really need that many computers. Then the use phase, 100 watts maybe, and say it's on 2/3 of the time. Maybe you turn it off when you go to bed at night. Some people don't. So that would be about 1.6 kilowatt hours per day per person. Phase disposal, hard to put a number on. So let's say we're going to keep it for 3 years. Then we have 1.6 kilowatts per day. We still have the 100 watts. That's on 1.6. Phase D, I still don't know. But the point is we use as much energy on resources and manufacturing as we do on use if you keep it for 3 years. So it's not insignificant to take this stuff into account. Now I have 3 personal computers because I want to work. Actually, I have more than that because I'm accumulating them. It's obscene how many I have. I have an iPhone, I have an iPad. I gotta have all these things, you know. One's for the dentist appointment and one's for aluminum cans. Ooh, I don't want to even read this. I drink about 3 to 4 cans of pop a day. It takes 0.6 kilowatt hours a day per person to make 1 can. And I waste 1.8 kilowatt hours per day. Yikes, that's huge. That's huge. Okay, I'm gonna switch to bottled water. Oops, that's not much better. 0.7, in fact, it's worse. 0.7 compared to 0.6, so if I drank bottled water, it'd be just as bad. So I think I should be drinking tap water. I could use styrofoam cups. I'm thinking I'm going to use a ceramic cup. So no more Coke for me, I guess. Junk mail. Yes.
Wait, a couple slides ago, did it say that
Tell me when to stop.
the one with the road repair,
Yeah?
4 kilowatt hours per day to repair roads, but yet a can is 2 kilowatt hours per day? I don't know.
Per person.
1 can is 0.6 kilowatt hours per day, and I drink a lot of cans of Coke.
So drinking 4 cans of Coke a day is the equivalent of repairing all of our roads? I don't understand how.
Our roads are 4 kilowatt hours per day. The Australian roads, well, the British roads were 2 per person. So part of it is that we have a lot of space. So when you do it per
All right, I
person,
didn't see the per person.
yeah, but it's never on here. I should go back and add it to all these slides, but they're all per people, and it's pretty sobering, isn't it? I had no idea how bad it was. Junk mail. Fortunately, we're getting less junk mail these days. It's all electronic. But it costs energy to make the junk mail and to print it. It costs energy to deliver it. McKay estimated 2 kilowatt hours per day. I think that this is high now. I don't know about you guys, but I get very little junk mail in a physical form anymore. It's all electronic. And then I just put all those bits in the landfill. Maybe even less these days. Batteries. Oh man, if there was ever a big engineering problem, this is what I tell when I go out to kids when I go out to high schools. Batteries are a huge problem because they're still heavy, they're still toxic, they still don't hold a charge forever, and we use them for all kinds of things. I hate to think how many batteries we go through. AA battery stores, 0.001 kilowatt hours per day. The energy to fabricate it is maybe 1.4 kilowatt hours. I don't know how to get around it. Say you throw away 2 per month, then the energy cost, not including the disposal, which we're going to talk about in a sec, is 0.1 kilowatt hours per day just for batteries, if you're throwing away 2 per month. Don't throw them away. I don't want to put them in a landfill because here's what happens. The outer canister corrodes, then there's nasty heavy metals inside there. They eventually get into the water table. That's bad for the environment. Nickel and hydrides that are in the batteries are semi-toxic. Lithium is explosive. Boom! So exploding landfills in my book is bad. So I'd like to recycle them. Here's how they recycle them. They burn off the combustible parts. Oops. Burning. CO2. I hope they're driving a turbine with that. Burn off the plastic and stuff, and then use a scrubber to reduce the pollution. Oh, there's energy in there. Then they chop up the cells. I'm guessing a big machine that runs on energy. Then they got to heat it up to liquefy the metal so they can burn off the other stuff, more burning. Then they cool the metal to a slag, and then they ship it to a recovery center. This is an energy-intensive process. I think it beats this, but it does take a lot of energy. So it requires 6 to 10 times the energy to reclaim the metals from a battery than to mine them in the first place. Plus all the burning and CO2 and packaging. Oh, there's another one. When you buy food, you don't just go to the vendor and there's a basket of chips and you scoop some out. No, you got to buy your own bag. They're all sealed and all these. And there's all kinds of packaging and a lot of things. You open up the box and then there's a package inside. And so embodied energy is maybe 4 kilowatt hours per day per person. That's a lot. What about other stuff? So these are harder and harder numbers to get a hold of. So McKay goes through and he says, well, the UK imports about 2 tons of stuff per person per year. And he says, suppose the average embodied energy is 10 kilowatt hours per kilogram. If you go back and look at the table for things you make your house out of, then you might say that that was a reasonable number. Here's an example of some materials. Fossil fuel, they import some of that. Wood, paper, glass, plastic, aluminum, steel. So 10, depending on how much of each of these things they import, 10 might be a reasonable estimate. That's where it comes from. So it works that out to about 40 kilowatt hours per day per person of stuff ow, I got this caught in my hair, ow. Stuff that they import. And then he adds on the car, the house, the packaging, the junk mail. His total estimate is 48 kilowatt hours per day per person. Now I found a site yesterday that said that the U.S. imports more stuff than any other nation in the world. So I don't know what our number is, but I think it's higher than 48K. Actually, I'm surprised though, because for England, I think they must have to import very much stuff because they don't have room to grow as many things, or they don't have as much manufacturing as we do. But maybe it's because of the per person. But still, I think that our number is going to be higher. I don't know what our number is. I'm sorry. How's it going to get to my house? Another big monster truck. Freight transport, so that's measured in ton kilometers or ton miles, depending on which side of the ocean you live on. Road in the UK, maybe 156 billion ton kilometers of stuff is shipped on British roads per day, or maybe that's per year. Doesn't say. Or 7 ton kilometers per person. The US, 1.3 trillion ton miles, or 2,000 billion ton miles, gulp, or 17 ton kilometers per person. So we're doing a lot of transporting. Of course, we have a bigger country. We have to ship things further, but more than twice what England has to spend. So UK will say 7 kilowatt hours per day per person road transport. US, 17 kilowatt hours per day per person. Having a port is very important. You don't have to ship things by road. So England's got water. We have some water. We also have a lot of space in between the water. In the 1700s, this is fascinating, it was actually cheaper to ship stuff from western Massachusetts, let's say the Berkshires, up the Finger Lakes, so this away, up the St. Lawrence and around Nova Scotia, or way out that way, and back to Boston. It was cheaper to do that than to put it on a wagon and go 50 miles. So for example, whiskey is concentrated corn. Whiskey tax fell especially hard on western farmers, had a whiskey rebellion. If you had a car from Japan, oh wait, I gotta show you this picture. Here's a map, okay? So I don't know why there's a star in Montreal, must be a Montreal map. Here's Massachusetts. If you wanted to ship that whiskey, you would actually be cheaper to go this way, go through the Finger Lakes, go up here, go through the St. Lawrence, go through the Gulf of St. Lawrence, all the way around Nova Scotia, here by ship, than to take it on a wagon that far. How amazing is that? Okay, if you get a car from Japan, my car came from Japan, 10,000 kilometers, 2 tons, so about 5,000 kilowatt hours to ship my car. So if it's good for 10 years, let's say I keep my car for 10 years, then it's 1.5 kilowatt hours per day just for the shipping. The average American owns 0.8 cars. Transport by water. The UK, 560 megatons of freight passes through their ports. I got the number for the US. I hope I put it on the slide. I found it yesterday. The intensity of a cargo ship, then, depending on how much it can carry, 0.015 kilowatt hours per ton kilometer. That's pretty low energy cost for shipping, as long as you got water where you need to go. US shipping, 600 billion ton miles. This is our domestic shipping. So I should get the number I found for our ports, which I hope I have somewhere, maybe I didn't write it down, and add that to this, and we would get our water shipping. But anyways, our domestic shipping is 0.08 kilowatt hours per day per person. Why is it so much less than our road shipping? Because we ship everything by road. We don't have that many waterways, especially if you want to get out west. So we don't ship that much by water domestically. But this number here doesn't account for international shipping. Rail. If you listen to NPR, you probably heard those commercials that say such and such a railroad company can ship, I forget how many tons, I forget how many miles on a gallon of oil. Does anyone remember the numbers? It's a huge amount. Turns out that rail is incredibly efficient. Who would have thought? We ship more stuff by rail than by road. How much does that energy consumption stack? Ooh, looks like it's going to be a homework problem, so I better not give it away. You can never have enough homework. And some other things that aren't taken into account. So we took into account how much energy do we spend heating water, but someone's got to pump the water to my... Stop that. Water heater. This is a very dangerous television antenna. Leave it alone. And you have to pump the water around. You have to treat the sewage. For McKay, he estimates 0.4 kilowatt hours per day per person. And here's the UK in their water consumption, and here's us. So I'm thinking our number is bigger than 0.4 kilowatt hours per day per person. Oh, and we pump oil and natural gas around a lot too. That's another 900 billion ton kilometers. How do you like this? Denali fault rupture, boom. So I'm thinking this is the Alaskan pipeline. 13 ton kilometers per person per day in the US, not included in McKay's estimate. Here's another poll. We use 660 billion cubic meters of natural gas per year. How many kilowatt hours per day per person is this? Okay, so at this point we're not whipping out our calculators, we're all taking random guesses. How many people want to guess 4? How many people want to guess 10? How many people want to guess 25? Nobody's biting on that one. How many people want to guess 65? Nobody thinks that. How many people want to guess 150? I don't remember. Oh, 65. Nobody guessed that. Whoa. 65 kilowatt hours per day per person shipping natural gas around. Oh, worth of natural gas. Not the shipping. That's how much we use. Wow. Cubic meter of gas has about 40 megajoules or 10 kilowatt hours. So we can do this calculation. Here's how many billion cubic meters. Here's this is people per year, blah, 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 blah. 70 kilowatt hours per day per person of natural gas energy that we use. Now we use it for some of the things that we've talked about already, just being clear. Our gas bills, we use therms. So maybe you have a 30 kilowatt hour natural gas bill. The therm is 100 cubic feet of gas. So far we have 40 kilowatt hours of electric plus 110 oil plus 70 gas kilowatt hours per day per person, 220 kilowatt hours per day per person in the US for energy. We've accounted for some of the ways we use the energy. This is just a different way of looking at the same data. And electric, of course, is double counting some oil and gas because we do burn limited amounts of oil and gas to make electricity. Just saying. Transport. Here is a plot of energy consumption. I need this thing. It's going to poke me in the head again. I'm trying to keep it away from my hair. Energy consumption, kilowatt hours per ton kilometer. This goes from 0 to 1.6. This is speed in kilometers per hour. So if it matters if it gets there fast, you want to be looking out at this end. Here is ships. Ships are 30 to 50 kilometers per hour. Very low energy consumption. If you can wait for it to come to you by ship, that's a great way to do it. Rail is faster and very low energy, very low energy. Road is way up here. Okay, it's about the same speed, maybe a little bit slower than rail because they have stoplights and the drivers have to stop and take a break. But it takes a lot more energy. If you want to ship things by air, well, you're not surprised by that. Here's a picture of a ship and a train and a road. And there's no picture of that's the airplane. It's so far away you can't see it. So I'm still working it out. The UK numbers were on the previous slide. I worked out for Ohio. I suspect our transporting stuff will be much bigger. I suspect our consumption of stuff is bigger, but I don't know. I don't have any data, just a guess, but maybe that's not right. Food and farming, so for these lights, gadgets, food, stuff, and transporting stuff, these are all McKay's numbers. I just added them onto our stack because I haven't figured out how they might be different for us. These numbers are very different for us, and then these numbers are different for us. And just to show you, this is McKay's stack on the same scale. So you see car and jet are the same It's the same scale here, and I squished their stack down. So notice that even using UK numbers, we're still way ahead of them in consumption. On the other hand, we're way ahead of them in potential generation by our wildly optimistic estimates, but his estimates are wildly optimistic too. And really, who expected England to be, a hotbed of renewable energy potential? Not me. So this is where I think we are so far. So the next time we'll talk about geothermal power. Comes from the earth is hot inside. You can take your Pop-Tarts down to the center of the earth and burn them to a crisp. So we'll do that next time. Are there any questions? All right, run and play.